In a parallel circuit, we use voltage E as the reference. In an RL circuit, the voltage leads, so the I sub L and B sub L are plotted along the negative y-axis. IT, or Y, the admittance, is on the hypotenuse, and theta and I sub L are at opposite sides. So you can see here from the figure we've got a simple RL circuit, and you can see the phasor representations associated with them. You'll notice that we have the phase angles outlined and the specific vectors or phasors for each of the components. So looking at an example, let's let the current through the resistor I sub R equal 30 milliamps and the current through an inductor equal to minus 20 milliamps. Find the current and the phase angle, express the total current in both rectangular and polar forms. So in this case, we're going to start with the definition of the tangent. Tangent theta is equal to the opposite over the adjacent. And in looking at the vectors itself from the diagram to the right here, you can see I sub L and I sub R form the opposite and the adjacent legs of the right triangle. So minus 20 milliamps divided by 30 milliamps gives us a tangent theta of minus 0.667. Taking the inverse tangent of minus 0.667, we get a minus 33.7 degrees as our phase angle. Now, again, we choose the trigonometric function sine theta because of the sides of the triangle that we have available that we're able to solve for. So the opposite over the adjacent, I sub L over the total I sub T, which is the hypotenuse. Moving our terms around, we get IT, the total current, equal to I sub L divided by sine theta. So minus 20 milliamps divided by the sine of minus 33.7 gives us a total current, then the hypotenuse, of 33.1 milliamps. Okay, so that forms our resultant. We interchange our terms here. We can call it the resultant. We can call it the hypotenuse. It just depends on how you want to relate the right triangle to the phasor diagram. So the total current then, rectangular, is equal to 30 milliamps minus J 20 milliamps. Why is it minus? Because it's in the negative direction, this yellow vector. The polar relationship then just becomes 36.1, which is our total that we calculated up here, and at an angle of minus 33.7 milliamps. Next example, let the total current equal 7.3 milliamps and our total current through the resistor equal to 3.6 milliamps. Find the current through the inductor, I sub L, and the phase angle. Express as rectangular and polar. So again, we pick the trigonometric function that matches what we're given, what we have here. So I sub R and the total current are givens, so we're going to use the cosine theta to calculate the first terms. So 3.6 divided by 7.3 milliamps gives us a cosine theta of 0.493. We take the inverse tangent of 0.493, of which we get a minus 60.5 degrees as our phase angle. From that, we're able to put together the polar current. 7.3 is our total. It was given to us up here at an angle of minus 60.5 milliamps, which is our phase angle here. Now we're going to take our definition. Again, the definition says sine of theta is equal to the opposite over the hypotenuse, right? So I sub L over I sub T. 7.3 milliamps times sine of minus 60.5 gives us minus 6.35 milliamps of current through the inductor. Putting that into rectangular form then, 6.3 milliamps divided or minus J 6.35 milliamps. Okay, in the next phase here, we'll take a look at circuit parameters as it relates to inductive susceptance. Again, we've got a relationship that we've kind of seen here before, and we need to understand what the difference is between this relationship.